Hello and welcome back to Gaffy's Grinds. This is video 7 in our organic chemistry video series. Today we're going to be looking at some properties of alkanes. So a reminder, in these videos we take ideas or concepts in Cert Chemistry, we break them down and try and make them simpler to understand, and we do some practice questions. Some tips for using these videos. As usual, we're trying to limit or eliminate all distractions. So you need to take your phone. You need to put it in a different room now where you can't be tempted to pick it up and check your social media or notifications. Close any other tabs that you have open on your computer, and just focus on watching this video and learning as best you can while you watch it. The most important thing is I'm going to ask you to do tasks. I'm going to ask you to do questions during the video. I'm going to ask you to pause and do the tasks. It's really important that you do those, otherwise you're not going to learn as much from the videos. Okay. So quick reminder, today we are talking about properties of alkanes. Now, before we talk about properties of alkanes, we have to remind ourselves of some things we learned a few years ago in junior cycle. Okay, so what we're talking about here is to talk about properties of alkanes, we first must revise our understanding of properties of any type of substance. So let's start off by thinking about what substances are made of. We know substances are made of particles. Now we can draw particle models to show us how the atoms or particles of a substance, atoms or molecules, are arranged. We draw them differently depending on the state, okay? So this would be an example of a substance which is a solid. Now most alkanes, or most organic chemistry molecules, most of them are not solids. Most of them are either liquids, which we draw like this, liquid, or gases, which we draw like this, gases. Now, quick reminder, what were these three things called? What were they called when we learned in junior cert? If you know, what I want you to do is I want you to speak your answer to the screen now. What do we call these three things at junior cert science? Okay, I'm hoping that you said we call them the states of matter. Now, our alkanes are an example of matter. Matter is anything which is made of particles. So technically, alkanes can exist as solids, liquids, and gases. Now, there's a couple of things we need to know. First of all, why are the particles arranged in such ways? So we can see that in a solid, the particles are arranged in predictable or regular rows. Okay, they have a regular arrangement. They have a repeating pattern. So 1, 2, 3, and underneath a perfect row, 1, 2, 3, and underneath a perfect row, 1, 2, 3. So that is a repeating pattern. We say they have a regular shape. Oh, sorry, a regular arrangement. Okay, means they have a repeating pattern. Now, solids are the only ones that have this. Liquids, while the particles are quite close together like they are in a solid, they have a random arrangement. Random arrangement, as do gases, also have a random arrangement. Now, another thing that we'll notice is if we take a look at the solids, particles are very close together, okay? So particles are close together. This is also true in a liquid, although they are not just quite as close, so they are not just arranged in with a repeating pattern. The gases, particles are far away. Lots of space between them. And what is this space? Well, we already know that this is just completely empty space. Okay, so it's not air, it's not any particular material, it's just empty space. Now, the question is, well, why do solids have a regular arrangement, and why are the particles close? Why are the particles also close in a liquid, and why are they not close in gases? Well, to learn the answer to that, why are the particles close together, we have to zoom in. What is between the particles? So when the particles are drawn really close like this, what holds them together? We say that there are forces of attraction holding the particles together. Forces of attraction. Now, these are not necessarily chemical bonds. This is not the same thing as within a molecule. If I have a molecule of, for example, O2, oxygen, two oxygen molecules. Well, I know that this is a chemical bond. Chemical bond. Chemical bonds are very, very strong. And this is not always a chemical bond. This is not always like, this can be a weaker force of attraction between molecules. So for instance, this is a chemical bond, but within oxygen, just going to move this for a second, but this here is two water molecules. And this here is what we call a hydrogen bond. This is a force of attraction between two particles of water. That's one particle of water, and that's another particle of water. These are not chemically bonded to each other, but they do have a force of attraction between them. So oftentimes, what we're talking about in these forces of attraction that are holding the particles together are these forces of attraction between molecules, not chemical bonds. Not chemical bonds. We are not talking about chemical bonds here. And the reason why we know this is when we warm up a solid, we can turn it into a liquid. Now, all we're doing there is we're overcoming these forces of attraction between the molecules. If we wanted to break these bonds here, this would take much more energy. This would take a very high amount of energy to break chemical bonds between two atoms. Those type of bonds are not easy to break, okay? But anyway, we're talking about forces of attraction between particles that we want to break or overcome in order to change from one state to another. Okay, so we're talking about forces of attraction between the particles. That's why in a solid, they're held together tightly. So we say that in a solid, forces of attraction are strong, or the range here is they can be strong to weak. And if we were to put them on a scale, we would say that the strong forces of attraction are usually a solid. The weaker forces of attraction are usually a gas for any particular substance. In a solid of the substance, so example, ice, if we're talking about water, the solid form of ice has the strongest forces of attraction between the particles. And in the liquid version of the substance, the forces of attraction are usually weaker, somewhere in the middle, and the gases, we have the least forces of attraction or the lowest forces of attraction. Okay, so it's the forces of attraction that we really need to overcome if we want to make them go from being in regular rows to less tightly held together. So here they are held together very tightly, and here not so tightly, and here very weakly they are held together. Now, how can we overcome these forces of attraction? Overcome? Question mark. How do we overcome them? Well, the answer is we have to add energy. We have to add energy if we want to overcome forces of attraction. So, very quick reminder then, if we have solid, liquid, gas, we have ways that we can change from a solid to a liquid to a gas. Quick reminder, these are called changes of state. These are physical changes, not chemical changes. So we're not breaking any bonds. They are physical changes. We are just breaking forces of attraction between the particles, or weakening forces of attraction by giving the particles more energy. So we're going to call this changes of state. So changing from a solid to a liquid. from junior cert. Can you remember what that's called? I want you to speak out your answer to the screen now, if you can remember, please. Okay, I'm hoping they said to go from a solid to a liquid. We call this melting. Okay, so now you've seen the first one done. I want you to pause the video and try and complete this diagram. So you should have an arrow here, you should have an arrow here, and you should have an arrow here. Okay, so pause the video, try to complete that diagram now, please. Okay, now I'm going to do this one down here. So the opposite of melting. So we've gone from a solid to a liquid, okay, by melting a solid. So take candle wax, we melt it, it turns into liquid candle wax. Now, what's the opposite called? If I'm turning from liquid candle wax back to a solid, what do I call that? Okay, we would generally tend to call this freezing. Okay, freezing, or sometimes it could be called solidifying. Solidifying, because it's a solid, we are making a solid, so solidify. But freezing is the word we usually use here. Okay, now, what about going from a liquid to a gas? This is something we should be familiar with. I'm hoping that you said, and either of these is true, evaporation. Evaporation tends to be slow and use energy from the environment. Slash, if we then take a liquid and we heat it up more quickly, we make evaporation happen more quickly. So we put a lot of energy in, we can get evaporation happen quickly. We will call this boiling, or there's actually one more word for it, vaporizing. Vaporizing. And why vaporizing? Well, vapor is another word for a gas. So all of these are correct terms here: evaporation, boiling, or vaporizing. This tends to be the hardest one, okay, from a gas back to a liquid. Okay, and we call this condensing. Okay, so if you need to remind yourself of that, if you didn't have a fairly good idea of that, pause the video and try and complete that now from memory. Okay, so if you didn't have a good idea, pause the video, try and complete that from memory. Okay, so you should only watch the video if you've tried to complete that diagram now from memory after me going through it. This is what you should have. Solid to liquid is melting. Liquid to gas is evaporation, boiling, or vaporizing. Okay, evaporating, boiling, or vaporizing. Gas to liquid, this is the hardest one. We call this condensing. And liquid to solid, we generally talk about freezing. Okay, now, one of these directions going from here to here involves heating, and one of these going from here to here involves cooling. So heating or cooling, which is which? So I want you to add those arrows to your diagram now and tell me which one is heating and which one is cooling. Okay, I'm hoping that you said to go from here, solid to liquid to gas, involves heating. And to go from gas to liquid back to solid involves cooling. Okay, underneath that, I want you to tell me in each case what's going to happen as we move along the arrow to the temperature. So actually maybe tell me where the highest temperature is and tell me where the lowest temperature is. So make it like a number line out of it. So a number line up here and a number line down here. Where's the highest and the lowest temperature on for each direction? Pause the video and add that now. Okay, so I'm hoping you should only be watching the video now if you have tried to do that for me. So going from here to here, if I'm heating, my temperature is going to increase. So solid would be the lower temperature. And when we heat it, it will obviously be a higher temperature. Okay, so if you weren't sure how to do that the first time, I want you to pause the video now and do it for this other arrow. Okay, so you should be watching the video now if you've completed this arrow for temperature. Well, again, if we're cooling, then it means we're starting at a higher temperature and moving to a lower temperature. So higher temperature, moving to a lower temperature. Okay. Now, for alkanes, we're mainly thinking about liquids liquid, and gases. So alkanes will mainly be either liquids or gases. Okay, so the main change of state that we're going to be talking about is from a liquid to a gas or from a gas back to a liquid. Okay, now we said that if you want to turn a liquid to a gas, what we need to do is we need to add energy. Okay, so we need to add energy to the liquid to overcome the forces of attraction. Again, attraction just means stick together or come together. So overcome the force of attraction. There's a force here that makes them want to stay together. And you add energy that makes it overcome the force of attraction. It gives them enough energy to spread apart. Okay. So when you add energy, you give them enough energy to overcome the force of attraction, and this lets them move apart from each other. So essentially, they have too much energy or enough energy so that the forces of attraction don't hold them together anymore. That's what you're trying to do. Now, it so happens that if we take alkanes, and I'm going to draw an alkane like this one, C single bond C, that's a alkane. Okay, now if we were to compare that to, say, a longer alkane, so this is a relatively short alkane, only 3 carbons. If we were to compare this to an alkane with 1, 2, 3, 4, 5, 6, 7 carbons, the thing is that the more carbon and hydrogens you have, the forces of attraction come from the electrons, okay? And the electrons are whizzing around inside the atoms, and they're creating these areas where there's a force of attraction. So essentially, this molecule, because it has many more atoms, has more electrons. It has more electrons moving around inside, which creates stronger forces of attraction. Okay, so essentially, if you have more atoms and more electrons, you get stronger forces of attraction. This smaller molecule has less electrons because it's got less atoms. So if it's got less electrons moving around, it's going to have weaker forces of attraction. Now that means attraction. If I was to draw molecules of this alkane, I would draw them with black circles. So say I've got 2 black circles stuck together. Okay, so the black circles here are the short chain alkane. And then I'm going to get a different color marker now to show the longer alkane. The red ones are the long alkane. Okay, now essentially what I'm saying here is that the weaker force of attraction, or the shorter molecules require less energy to overcome these weaker forces of attraction. The longer molecules require more energy to overcome the greater forces of attraction. Okay, so if I have to put more energy in, this is going to result in it taking longer to get it to change state. I have to add more energy. So in other words, I have to get the temperature higher. So higher temperature. If I have to add less energy to get these ones to break apart or to overcome the forces of attraction, then I would say it happens at a lower temperature. I need less energy. Now, lower temperature. Now what I'm trying to do is I'm trying to change the state. I'm trying to get it to go from a liquid to a gas. That is called boiling. So the temperature, if I have to go to a higher temperature to get these ones to overcome the force of attraction. The temperature that I'm talking about, apologies, the temperature that I'm talking about is what we call the temperature at which it boils. The temperature at which it boils. Okay, so the temperature at which it boils, this is known as the boiling point. We've probably heard that phrase before, boiling point. Now, why is it boiling? Why it's got to do with boiling? Because it's got to do with turning from a liquid to a gas. Why is it a point? Point just means the temperature. Okay, so it's the temperature at which a substance boils. So let's just recap. Bigger molecules, represented here by the red dots, require more energy to overcome the forces of attraction. So bigger molecules have stronger forces of attraction, require more energy to get the particles to come apart, basically, to overcome the force of attraction. If it needs more energy to do this, you have to get it to a higher temperature. The temperature we're talking about is the temperature at which it boils, because when the liquid boils, it lets the particles move apart. So they move apart from each other and they're not connected anymore. So to do this, you have to put enough energy to overcome the forces of attraction. And this temperature at which a substance boils, we call the boiling point. Okay, so a general rule is bigger molecules have higher boiling points when we're comparing two of the same type of molecules. Remember, these are both alkanes. Now, for a smaller molecule like this one, propane, has weaker forces of attraction compared to this one, shown with the black dots. That means it needs less energy to overcome the forces of attraction and let the particles spread apart and turn into a gas. If it needs less energy, I can do this at a lower temperature. What temperature are we talking about? The temperature has to do with, we call this the boiling point, temperature at which we turn it from a liquid to a gas. Okay, the boiling point, if it's at a lower temperature, the boiling point we say is lower if we've got weaker forces of attraction. So a general rule, and this is really relevant and really important for the practice questions that are coming up. A general rule, well, first of all, what is a boiling point? Boiling point. Okay, so you guys should now be able to explain what a boiling point is. Pause the video, try and speak your answer to the screen now, please. Actually, just speak your answer to the screen, the boiling point. Okay. Okay, so I'm hoping that you said that the boiling point is a temperature, first of all, is the temperature at which a liquid turns into a gas. That's the definition of what a boiling point is, the temperature at which a liquid turns into a gas. We will see boiling points again in more detail just a little while. Now, a general rule that we would have is that generally small molecules or in this case, what we're talking about is short chains, because we're talking about chained alkanes. What's the general trend that's going to happen if we compare them to larger molecules? Okay, which are, in other words, longer chains. And we're talking about alkanes. Now, the real question here is you have to start thinking about, okay, well, what are the forces of attraction like? Well, if we have larger molecules, we have more atoms, we have more moving electrons, we're going to create stronger forces of attraction. So the boiling points, if we're comparing shorter molecules with longer molecules, we're going to have lower boiling points versus higher boiling points. That's a general rule. So smaller chains or shorter chains will have lower boiling points versus longer chains, which will have higher boiling points. Okay. Now, another idea that I want to talk to you about is the idea of another property of solids, liquids, and gases is whether a substance can flow. Okay, what does flow mean? Flow. The idea of flow, we know that a river is flowing. If we take a river, we know that it's flowing. What does this mean? Well, it means that all the particles in the river, if these were water particles, flow means that they generally all start to move in the same direction. So a river is flowing in a direction. It means that the particles are generally moving all in the same direction. So particles can be moving in a substance, but not all generally moving in the same direction. So when we're talking about a flow, we're talking about, in general, a lot of the particles are going one way or the other. A lot of particles are going in the same direction. Now, viscosity, I want to introduce a word, the viscosity of a substance. Okay, so if we take substance A and substance B, okay, and if we set up a little ramp, okay, so we have a little ramp, and we've got substance A and we've got substance B. Now, if we're going to test, we're going to drop some particles, a couple of particles of substance A and a couple of particles of substance B. If we were measuring viscosity, we'd be talking about basically how fast can they flow down a ramp. So if substance B moves fast and substance A doesn't move fast, we would say that A has so the substance which is slower to flow is a thicker substance. So viscosity really means how thick. So how thick, in other words, so thick substances don't flow easily. An example of this would be something like honey. Honey is reasonably viscous. Okay, it's quite viscous if we compare it to something like water. If we pour a glass of water out into the sink, the water the particles of the water, so imagine if this is water, substance A, and this is honey, substance B. If I was to ask you, well, which one, if we were put the particles at the top of the ramp and to let them flow, which one would flow quicker? Well, the particles of the water would generally tend to move down the ramp all together. They would flow. We'll call this flowing. Particles move in one direction down the ramp. The water particles can flow quite freely, quite quickly. The honey particles, though, they will eventually get to the bottom. They will eventually flow. Okay, so we call this water is a fast flow. We would say then that the honey is a slower flow, slow flow. So the particles do move in that direction, but they take longer for it to happen. So we'd say that honey is more viscous because it's slower to flow, whereas water is less viscous. Now, why though? Well, it's the same reason that we were looking at when we were talking about boiling points. The forces of attraction in water, if we were looking at water, we would say the forces of attraction are weaker forces, which allows them to move more easily, move more easily. The honey forces of attraction are stronger forces, which means they do not move as freely. Now, if you think back for me, back to large hydrocarbon chains versus short hydrocarbon chains. We said that shorter hydrocarbon chains are like the water here. They have weaker forces. Therefore, they will move more easily, they will flow better, and they will be less viscous. The longer chain hydrocarbons have stronger forces of attraction. We learned that already. That means they do not move as freely. They will be more viscous. They will be thicker. They will flow more slowly. Okay, I know that's quite a lot to take in. Okay, so let's return to our summary table and see what we know now. Okay, so we have large molecules. Oh, sorry, we'll start with short. We have short chains and we have longer chains. And we have boiling points. And we would have viscosity. Okay, so short chains, we know, because they have weaker forces of attraction, have lower boiling points. Longer chains have more forces of attraction, so they have higher boiling points. The viscosity has to do with how freely can the particles move and flow. So lower forces of attraction in short chains means they have a lower viscosity. Okay, now what does that look like? It looks like runny, like water. They can run very quickly, they can flow. Longer chains compared to short chains have a higher viscosity. So what does that look like? They look more thick, like honey, if you think of honey. The last thing I want to talk about before we do some practice now, okay, I know this is a lot of stuff to take in. I'm going to let you take down this table as a summary in a minute, is flammability. So in other words, how easily is it to set them on fire? Okay. Now, I'm just going to flip this over to explain this one. Okay, so we know we're talking about hydrocarbons. Hydrocarbons are substances with hydrogen and carbon only. So hopefully you realize that in an alkane like this, there's only two types of bonds. There is a C bond, and there are CH bonds. So if I was to take a longer hydrocarbon over here, maybe 6 carbons versus 3. It also has only C bonds and CH bonds. Now, as a fraction of the molecule, see this here, as a fraction of a molecule, well, actually, before I go there, sorry, it so happens that the C bond has a very low amount of energy compared to a CH bond, higher energy. That means that when we break CH bonds, we can release a lot of energy, because however much energy is stored in this bond, when we break it, when we do a chemical reaction like burning, and we break those bonds, we release all that energy. Energy when burned, or when we do any chemical reaction. Now, this is approximately 400 kilojoules. That's how much energy is in here. Whereas this is approximately 90 kilojoules. So as you can see, this is much, much higher. So these bonds, the CH bonds, are why these things release so much energy when we burn them. So when we take these and we burn them, we get energy from them. That's why they're so useful. Why are they useful? Why is there so much energy? Well, it's because of these CH bonds. This is quite a low amount of energy. If it was all CC bonds in the whole molecule, there was no CHs, this would be pretty useless as a fuel, because you have to put energy in to break the bonds, and then basically you're not making much more energy back from it. So the 90 kilojoules for each carbon bond you break is not that much, whereas 400 kilojoules for a CH bond is much more. So as a percentage of this molecule, the CHs make up a higher percentage. Whereas here, the ratio of CC to CHs, the CHs make up a lower percentage here. A lower percentage, because there are many more CC bonds. So you're really desiring to have much more CH bonds. Sorry, I know this is a little bit complicated. I'm trying to explain it as simply as I can. But the idea here is, because the shorter chains have a higher proportion of CH bonds to CC bonds, then they are more, this makes them more flammable. They will catch fire more easily because the CH bonds are much more energy, they've got much more oomph than a CC bond, okay? So because CHs make up a higher percentage in a smaller molecule, say if we take an even smaller one like methane, CH, this will have even more, this will be the most flammable of all the hydrocarbons because it's only got CH bonds. It doesn't have any CC bonds, so it's a very high percentage of CH bonds. So this will be the most flammable, and the longer our chain gets, the more of the molecule is taken up by CC bonds, which are lower in energy and they're not as flammable and efficient. So more flammable if we've got short chains, less flammable when we've got longer chains. That's the trend you have to remember. I've tried to explain why. I hope I've done an okay job, but I don't want to spend too long because we're already on this video quite a long time. So flammability for short chains is actually higher versus low flammability in the longer chains. Okay, so if you've got say a hydrocarbon that's 300 carbons long, then that is going to be nowhere near as flammable as a hydrocarbon with 2 carbons long. Okay, so what I'm going to get you to do, guys, I'm going to get you to pause the video and take down this summary table. Okay, so pause the video now and complete that summary table, please. Okay, it's time to do some practice now. So we are going to throw up the questions here, and you guys are going to do the questions for me. Okay, so these are the questions. Okay, so I'm going to get you to pause the video and try those first 6 questions there for me now. Okay, so you should only be watching the video if you have tried those questions out. Okay, I'm going to throw up the answers now. Okay, so the first question said alkane X and alkane Y are tested against each other. Alkane X is a lot easier to set on fire than alkane Y. Which one has a longer chain? All right, so the correct answer there is alkane Y has the longer chain. Okay, so if alkane Y was harder to set on fire, that must mean that it's got a long chain because long chains have lower flammability. Alkane X and alkane Y are tested against each other. Alkane X is a lot easier to turn into a gas than alkane Y. Which one has the longer chain? Which thing is this about? I'm hoping that you realize that this is about the boiling point. So if alkane X is easier to turn into a gas than alkane Y, that means alkane Y has a lower chain. Okay, I'm hoping you got that right. If you didn't, you need to go back to the bit where we talked about the boiling points. You then have a table. Below are the boiling points of a number of alkanes. Put them in order of increasing chain length. Okay, so you have boiling points and you have to put them in order of increasing chain length. This is the correct order you should have. Oh, sorry. B, then E, then D, then A, then C. Well done if you got that right. Okay, so B has the lowest boiling point up to C has the highest boiling point. Okay, so short chains have the lower boiling point. So the lowest boiling point was -28 for B. That's got to be the shortest chain. And the longest chain has to be the one that was the highest boiling point. 2 students investigated the viscosity of alkane X and Y. They put a sample of each alkane at the top of a ramp and they see how long it takes to flow down. How long would you expect the amount of time taken to flow down to relate to the length of the chain? Well, hopefully you realize the pattern. Longer chain means a larger amount of time to flow down. So the longer chains are more viscous, which means it takes them longer. Explain your answer to explain your answer to question 4. Why is this the case? Well, longer chain means longer chains have higher viscosity and they do not flow as easily as short chains. So if they do not flow as easily as short chains, then they will take a longer time to reach the bottom. A mixture of alkane D and alkane E from the table above is heated to 30 degrees. Explain why alkane E turns into a gas, but alkane D does not. So if we're at 30 degrees, well, alkane E boils at 23. So we have gone past the boiling point of E. So we say that the boiling point of E has been reached. Now, boiling alkane D does not boil until 65 degrees. If we are at 30 degrees, we are not at the boiling point of D. So the correct answer here is E turns into a gas because its boiling point has been reached, but the boiling point of D has not yet been reached, so it does not turn into a gas. Okay. Okay, just a little addition now before you try the next little set of practice questions. The boiling point we've already learned is the temperature at which a substance turns in from a liquid to a gas. Now, we can plot this on a number line, okay? So we can plot this on a number line. And the number line shows the temperature, temp. And obviously, going from the bottom to the top here is an increasing temperature. Now, what we can do here is we can put some temperatures along here, okay? We can put a line that represents the boiling point. Sorry, this would be the melting point. Melting point. And at the top, we can put another line that represents the boiling point. Now, each substance, when we can do this number line for any substance, okay? What's important to remember is that if we're below the melting point, so if the temperature is below the melting point, it will be a liquid. Oh, sorry, not a liquid, that's incorrect. It will be a solid. In other words, the temperature is colder than the melting point, so it hasn't melted yet, so it's a solid. Once it's melted, but before it boils, so it's melted, it's a liquid, but it hasn't boiled yet, it's still a liquid. All in this range here will be, the substance will be a liquid. And then once you increase the temperature even more and you go above the boiling point, it will be a gas. Okay. Now, each substance will have its own melting point and its own boiling point. If we take water as an example, water, the substance water up here in the corner, has two temperatures we need to know. It has a melting point of 0 degrees C, and it has a boiling point of 100 degrees C. And what that means is if we're below 0 degrees, so say a temperature like -20, if we're at a temperature like -20 degrees C, well, that's on the number line below 0. That means the substance would be a solid at -20 degrees. Okay, so -20. If we were to take that substance from here and we heated it up, it would stay a solid all the way up until you get to 0. Then when you go above 0, it's turned into a liquid. So water would be a liquid all the way until you heat it up and you get to 100 degrees. Then we get another change of state. And when we go above 100 degrees, we then have water as a gas. Okay, so that's what we're doing. Heating it up from a solid, it reaches its melting point, it turns to a liquid. Then it goes up, it reaches its boiling point, it turns to a gas. Now, what you might not have ever considered before is when we cool it down, we're above 100. So say we start at a temperature like 120. So we're a gas, water as a gas is called steam, and we cool it back down. Notice that it's the same temperature when we get from a gas back down to 100 degrees. That's the temperature that it turns back into a liquid. What do we call a gas turning back to a liquid? What's the name for that process? Speak your answer out on 3. 1, 2, 3. I'm hoping you said condensing. And as we cool it yet more, all the way back down to this point, at 0 degrees, it would then turn back into a solid. We could keep cooling it beyond that, so on. Well, this actually means that the boiling point is technically then the temperature that a liquid turns into a gas, or it's also the temperature that a gas would turn back into a liquid. So that's an interesting point that you might not have considered before, that the boiling point will be the temperature we turn from a liquid to a gas, but also the same temperature a gas would turn back into a liquid. So for water, it turns from liquid to gas at 100 degrees. But then when we cool it back down to 100 degrees, it turns back into a liquid. So it depends whether we're heating or cooling. If we're heating and we're below 100, when we get to 100, it turns into a gas. If we're cooling and we're above 100, when it gets back to 100 and we keep cooling, it turns back into a liquid. So that's something you might not have considered before, but it's important if you're going to be able to answer the next set of questions. It's a good idea if you're ever stuck to figure out what state a substance is at or where the melting and the boiling point is. If you draw a simple number line like what I've done there for your substance, so obviously your substance will have different melting and boiling points. This is only for water. only for water are these numbers. Your numbers could be different than this. They might be 72 degrees as the boiling point. If it's or 78 degrees would be alcohol's boiling point, for example. If you're given the numbers, you can put them on a number line and you can figure out what state they will be at using a simple number line like that. Okay, so with that in mind, I've got some more questions for you to practice. Okay, so what I want you to do is I want you to do these questions now, please. Okay, so you've got a table up at the top here. I'm just going to move this little guy out of the way. You've got a table up at the top. It's got 5 alkanes with 5, and each alkane has a boiling point. Okay, and you have to answer the questions that relate to this table. Okay, so answer questions 1 to 8. Okay, go ahead and do that now, please. Oh, pause the video and do that now. Okay, so you should only be watching the video if you've tried questions 1 to 8. Answers are coming up now. Which alkane has the highest boiling point? Hopefully you can see without me flicking over to the answers that should be C. So alkane C has the highest boiling point. The alkanes are heated to 500 degrees. Explain why they all turn into a gas. Okay, well, they all turn into a gas because we have reached all of their boiling points. So 500 degrees is higher than any of them. So they have all reached their boiling point. That's going to be your answer there. From the temperature of 500 degrees, they are then all cooled down. Which one will condense first? This one is a little bit tricky. Okay, you might have said B because it looks like, oh, B is the coldest, but that's not what we're doing. Remember, we're up above 500 and they're all gases. And we want to know, if you look down here where I'm pointing, we want to know which one turns into a liquid quickest. So it's going to be, they're going to turn into liquids at their boiling points again. Okay, so it's actually going to be the one with the highest boiling point, which is C. If you're not sure how to do that, you need to take out, you need to do what I've done here and draw a number line to see how that works. Okay, go back in the video, watch the number line and figure out how that one works. Explain how your answer to question 3. So the answer to question 3 is that a substance will turn into a gas at its boiling point when heated and back into a liquid at its boiling point when it's cool. So because C had the highest boiling point here, 430, it will turn back into a liquid at 430 when we're cooling down from 500. The other ones will still all be gases until we get back to their boiling point. Which one will condense last? Well, this one is going to be a gas all the way back down to minus 28. So all the rest of them will be back as liquids as we cool down to their temperatures. But this one will still be a gas all the way down to minus 28. So this one will condense last. Explain your answer to question 4. Well, that should say question 5, sorry. Explain your answer to question 5. B will condense last. Why? Well, B has the lowest boiling point. It won't turn back into a liquid until it's cooled all the way down to minus 28. Okay. Compared to D, predict the viscosity of A. So A has a higher boiling point than D. That means that it's a longer molecule. Okay, so larger molecules have greater boiling points. Now, longer molecules are also more viscous because they've got more forces of attraction. So compared to D, predict the viscosity of A. A would be more viscous than D. Well done if you got that right. Now compared to B, predict the viscosity of C. Very low boiling point, much higher boiling point. So higher boiling points means bigger molecule because there's more forces of attraction in a bigger molecule. Now, more forces of attraction in a bigger molecule, that means if it's a bigger molecule, it will be much more viscous than this one. Okay, so the viscosity of C is more viscous, much more viscous than B, much more viscous. Okay, a few more questions here. Same table, same information. Pause the video, try the questions. Okay, so you'll only be watching the video again if you have tried all these questions 9 to 16. So a mixture of A and D are heated up until they turn into a gas. Predict the temperature at which this will happen, or at which this might happen. Now, no, it's not a mixture of the two temperatures. It doesn't work like that. What happens is that when it reaches the first boiling point, which is 65, D will turn into a gas. Okay, what's going to happen then is at 91, A will turn into a gas. So technically, you're going to start turning into a gas at 65, and you're going to keep turning into a gas until you get to 91. Okay, so what I have written here is starts at 65 and finishes at 91. Okay. 10. A and D are cooled down to a temperature of 80. Which one will condense? Well, hopefully you can see that the boiling point of A is 91. That means it will turn it into a liquid again at 91. Okay, it turns into a liquid at 91. D won't turn back into a liquid until you cool it down to 65. Now, if we're at 80, we haven't cooled it down to 65. So the one that will condense will be 91. So why will 91 condense? A will condense is the answer there. And explain your answer. Why will A condense? Well, we have cooled it below its boiling point. We have not cooled D below its boiling point. 11. A mixture of alkanes is cooled down to, of all these alkanes is cooled to 0 degrees. Which one is still a gas? Well, B is still a gas all the way to -28. So we haven't got that cold yet, so it's still a gas. The answer is B. Alkane C has 15 carbons. How many hydrogens does it have? Well, it's an alkane. That means its general formula is CnH2n plus 2. So if C is 15, then H is going to be 2n plus 2. 2 15s plus 2 is 32. So we've got 32 hydrogens. Write out its chemical formula. It's going to be C15H32. Well done if you got that right. I'm hoping that's pretty easy. Alkane A has 11 carbons and E has 5. Predict how many carbons D has. Well, A has a boiling point of 91. E has a boiling point of 23. D is somewhere in the middle, 65. It's about right bang in the middle. So we're going to say it's a number of carbons in between 5 and 11. So we're going to say 7 to 8 carbons, 7 to 8 carbons, somewhere in that range. So if you wrote that, well done. At what temperature does gaseous D condense? So if D is a gas and we're cooling and we're condensing it, what does condense mean? Say your answer to the screen on 3. 1, 2, 3. It means a gas turning back to a liquid. Well done if you said that. So what temperature does the gas D turn back into a liquid? Well, it turns back into a liquid at its boiling point, which is at 65. Well done if you got that right. Last question. Explain how you can use the boiling points of D and E to separate a mixture of them. Well, D and E have quite different boiling points. E boils at 23, D boils at 65. So if we heat a mixture of these two to 23 and allow E to evaporate or to boil, we can then collect E and we get left behind. D has not yet boiled, so we keep D as a separate liquid. So the correct answer, heating a mixture to 20 degrees. So only E boils and can be collected. D does not boil and instead remains a separate liquid. There are the answers on the screen. If you need to pause and make any corrections, do that now. And there was 1 to 8. Sorry, I should have done this before, but there is 1 to 8 if you need to pause and make any corrections now. Okay, guys, I appreciate that was quite a long video, but it was quite important that we understand the properties of alkanes to help us better understand the next process we're going to be talking about, which is how we take crude oil, which remember was a mixture of all these alkanes, and we separate it. Well, we really need to understand how boiling points work on what we did today to help us understand how that process happened. So that's what we're going to be looking at the next day. How did they take crude oil and separate it into its different alkanes? Okay, so I'll see you in the next video.